Hello everyone and welcome back. So today I will be doing a review of sorts of trigonometry. That is, I'll be going over most of the formulae that are there in most trigonometry courses or chapters in when you take maths courses. And I'll be trying to give a proper justification for each of these formulae, and I'll be also deriving some common results that are used throughout trigonometry problems and courses. And I'm also thinking that I'll do a similar video on derivatives. And actually, this video is the first of a two-part mini series of sorts. In this video, I'll only be deriving the fundamental formulae, and then I'll be using these formulae in the next video to derive the most of the other formulae that are present in the chapter or whatever course that you're taking. So I will try and proceed as slowly as possible because I've seen many people actually get overwhelmed with all the formulae that this chapter has to offer. So let's begin at what I believe is the most basic thing that we can talk of, and that is, let's check whether sine and cos are even or odd functions. Now, if a function is said to be odd or even, that is, if it's said to be odd, if f of minus x is equal to minus f of x, and a function is said to be even if f of minus x is equal to f of x. And by the way, I'm assuming that you know the very basics of trigonometry, that is, what is sine theta being? Sine theta being is equal to opposite by hypotenuse, cos theta is equal to adjacent by hypotenuse. I won't be going into the very basics. I'm going to assume that you have sort of a working knowledge and that you're hoping to expand your knowledge on trigonometry. So just looking at this circle over here, we can see that sine alpha can actually be written as AC by OA, and this is actually a unit circle over here. So OA is actually just equal to 1. So we can write sine alpha is equal to AC, and that's it, because OA is equal to 1. However, sine of minus alpha is equal to BC by OB, and we consider the distance to be always positive. But over here, we actually see that since this is the coordinate axis, we see that this is actually a negative distance, and this will be equal to the distance AC. So this is actually equal to minus AC. And so we actually see that this is in fact an odd function. Similarly, you can try and check it with cos alpha, and cos alpha will actually be over here is just going to be equal to OC, because OA is 1. However, cos of minus alpha is still going to be equal to OC, because over here is going to be OC by OB, and so the x distance has not changed. But in the case of sine alpha, the y distance has actually become the negative of its value. That's why we get this negative sign over here. So we can actually write this as cos of minus alpha is equal to OC. So we actually see that this is an even function. That is, f of minus x is just equal to f of x. So this is what I would consider one of the basic properties of these sine and cos functions, and these actually prove useful when you're trying to derive the compound angle formulas and things like that. Now we'll move on to another very important property of the sine and cos functions, and also while I'm only going to do these derivations for mostly sine and cos, and I'm assuming that you will try and do this from tan and cot and cosec and sec by yourself as sort of an exercise. So just keep that in mind. Now over here we'll try and look at what sine beta will be, right? This is right angle triangle, so sine beta can be written as AC by AB. No, sorry, AC by BC. Alright, and now let's try and see what sine alpha is. I'm just going to write all the sine and cos values that we can write. So sine alpha will be equal to AB by AC, and cos alpha is going to be equal to AC by BC, and cos beta is going to be equal to AB by BC. And of course, if you feel that any of this is too slow for you, feel free to like fast forward the video and things like that. So let's try and see what and we can also write alpha plus beta plus pi by 2. We're going to, this is a 90-degree angle, so we can actually write pi by 2 is equal to pi. That is, the sum of the angles of a triangle is equal to 180 degree if you still comfortable with using degrees. So we can say that all of these angles sum up to 180 degrees, or they all sum up to pi radians, and we can actually take this to the other side and we can say alpha plus beta is equal to pi by 2. So now over here, if I try and write a say sine of pi by 2 minus beta, that is nothing but sine alpha. And if you see closely, you can actually see that sine alpha is nothing but cos beta, and cos alpha is nothing but sine beta. So we get a very important result over here, and that being sine of pi by 2 minus any angle is equal to the cos of that angle, and similarly cos of pi by 2 minus say any angle, I'll just write say alpha over here, this over in this case will be equal to sine beta, which is actually equal to, oh sorry, it will be equal to cos beta, my bad, it will be equal to cos beta over here, and that will be equal to sine alpha. And so this is for the specific case when we have pi by 2 minus some other angle. The special case, the general case in which we have pi plus alpha, pi plus beta, or 3 pi by 2 plus alpha, that I will attempt to explain using the unit circle in the next video. So if you're interested in that, you can check the next installment of this mini series. So these are two very important properties of the sine and cos function. Now along with this, there's also a very important identity that is used almost everywhere in trigonometry, and that actually involves squaring these and trying to find a result. Okay, so over here I'm going to try and square, I'm just going to rub all of this for a moment over here. So I'm going to square both the sine and cos functions of the same angle and see if I'll get anything. And so over here we'll actually be using the Pythagoras theorem, which basically says that the sum of the squares of any two sides of a right angle triangle is actually equal to the square of the hypotenuse. So just quickly squaring sine square alpha, let's see what we get over here. Sine square alpha is actually equal to AB square by BC square, right? And similarly, cos square alpha is equal to AC square plus AC square by BC square, my bad. And so when I sum these two values, I'll find that sine square alpha plus cos square alpha is equal to AB square plus AC square by BC square, right? AB square plus AC square by BC square. Now we know from the Pythagoras theorem that AB square plus AC square is nothing but BC square itself. So we can write this as BC square by BC square is actually just equal to 1. And this result is something that's stated almost everywhere in trigonometry, and it's insanely useful even when you're doing problems that involve a lot of other formulae. Now, if you divide this expression by cos square alpha, you'll actually get, suppose I can write this as sine square alpha by cos square alpha plus, I'll just drop this off, plus, that doesn't look like a plus sign, plus cos square alpha by cos square alpha, so this will be nothing but 1, alright, and I can write this as 1 by tan square alpha, cos square alpha. So this becomes 1 over here, and this is actually sine alpha by cos alpha the whole square, which is nothing but tan square alpha. and 1 by cos square alpha is nothing but c square alpha. So we get yet another important identity, that is tan square alpha plus 1 is equal to sec square alpha. So this is yet another important identity, and there's a third another important identity that you will get by dividing the whole expression by sine square alpha. So I will leave that up to you, and let me know what result you get. Okay, so now we will move on to the derivation of the compound angle formula, which is what I believe something that troubles most people, and this is actually the first thing that most 11th graders in the CBSE curriculum are exposed to, and they find this to be very challenging, and because there's a lot of formulae that are actually derived from the compound angle formula. So you'll actually be looking at how to derive this formula, and you'll actually be doing two different proofs. One is for the cos compound angle, and this one is for the sine compound angle. Although you can get one or the other by simply uh, manipulating by using the pi by 2 expression, I feel it's good to give you both proofs and see which one you prefer. So let me just move this thing down here so I get some space to work with. I'll move this thing down, and so we'll start deriving it. So over here, let's just take in the figure for a moment, pause the video if you have to. So over here I have drawn an angle alpha, and then there is an additional angle beta over here, and then I've also drawn an angle beta in the other direction, that is in the clockwise direction. And in trigonometry, clockwise angles are negative and anti-clockwise angles are positive. So this angle over here is actually minus beta, and this is not something that you would think of intuitively. We have actually drawn this in order to specifically get the formula. Alright, so keeping that in mind, I think hold on, my bad. This line should actually be drawn till over there. Yeah, it should be connected over there. Okay. So now we'll actually try and look at triangles ODC. Okay, triangles ODC and triangles OAB. And in this triangle, we are going to look at, we're going to try and establish some sort of relation between them, whether they are similar or whether they are congruent. So we see that they have the same angle alpha plus beta. You might argue that this is in fact alpha minus beta, but here we're interested in only the magnitude of this angle over here. We're not talking about the direction specifically when we talk about these triangles. So we see that this angle alpha plus beta is equal. So we can write that angle AOB is equal to angle angle COD, and we also see that OD is equal to OB and OA is equal to OA is equal to OD and OB is equal to OC, because they are all the radii of the circle, and that is equal to 1 because you're talking about the unit circle over here. So we can actually conclude that, let me just write that as well, OD is equal to OA, and we can say OB is equal to OC. So we can say that by SIS criteria, triangle ODC is actually congruent to triangle OAB, triangle OAB. And as a consequence of this, we can actually say that CD is equal to AB, which is the result that we'll use in our proof. So that's why we actually wanted to find a relation between these two triangles. So using that, I'm going to try and find what this length CD is and what this length AB is, and then we're going to equate these two lengths. So the length CB can actually be found using the distance formula, and that is nothing but before that, let me write the distance formula itself. The distance between any two points can actually be written as the square root of x2 minus x1, that is the difference in the x coordinate of the 2 points, the whole square, plus y2 minus y1 the whole square. That is the difference in the y coordinates of the 2 points. So in the case of CD, and let me write CD square so we can get rid of the square root. We can write this as the x coordinate of OC will be 1 because it's a unit circle, so 1 minus, and x1, that is the coordinate of D, x coordinate of D. Now if you'll actually look at this, you can see that this distance, if you draw a right angle triangle over here, this distance is nothing but cos of alpha plus beta. So let me write that over here, and we'll square this over here, plus, and y2 over here is 0, so we'll write 0 minus y1 is actually sine alpha plus beta, so we can write that as well, sine alpha plus beta the whole square, and this is all in the bracket. So we can expand the square. This will be 1 minus 2 cos alpha plus beta plus cos square alpha plus beta plus sine square alpha plus beta. Although this was minus over here, it's a square, so we can get rid of these minus sign. And like I just told you, the formula that we just saw over here is very useful, the sine square alpha plus cos square alpha. That is, if we have the same argument in the cos function, we can simply equate this expression over here to 1. So CD square is actually equal to 2 minus 2 cos alpha plus beta. Okay, and so I'll have to move this thing even further down. So let me just do that over here. So now we'll try and find the distance for AB, that is. Now AB square again, because I just want to get rid of the square root. We can write that as x2 minus x1. So that over here is actually, if you draw a perpendicular, you'll see that this is nothing but cos of minus beta. So this is cos of minus beta minus the coordinate for A is actually cos alpha, so minus cos alpha, and we'll square this quantity. And similarly, this will be sine of minus beta sine of minus beta, right, and minus sine of alpha. Okay, so if we square this whole thing, we'll have to get a bit more space over here. This will be, again, like I said in the earlier, I took time to derive the fact that cos is an even function and sine is an odd function, because we'll actually be using it over here. Since cos is an even function, we can say that we don't need a bracket over here. We can say that cos of minus beta is equal to cos beta, and this is simply cos square beta minus 2 cos alpha cos beta plus cos square alpha, and this is actually equal to minus of sine beta. And if I take the minus sign common, I can actually write this as sine square beta plus sine square alpha plus 2 sine alpha 2 sine beta. And this is our expression for AB square. And since AB square is equal to CD square, I am going to equate this expression over here and this expression over here. And again, we have a cos square beta plus sine square beta and a cos square alpha plus sine square alpha. So I'm just going to write that as 1 plus 1, and I'll just write the whole expression as 2 minus this whatever else is there. So I will write 2 minus 2 cos alpha plus beta is equal to 2 minus 2 cos alpha cos beta plus 2 sine alpha sine beta. This is supposed to be multiplication. Alright, so we can cut the 2's, and we can take the minus sign out, and we can cut the 2's everywhere as well. So hold on here. So this expression actually turns out to be cos of alpha plus beta is equal to cos alpha cos beta. Oh, hold on, this is actually negative sign over here. Cos alpha cos beta minus sine alpha sine beta. And this is yet another very important formula in trigonometry. That is, what is the cosine of two different angles when they are added in terms of the cosines of the and sine of the individual angles. So let's just try and verify if this formula actually works and if we didn't make a mistake. So if I take suppose alpha is equal to pi by 6 which radians, which is this 30 degree, and if I take beta as pi by 3 radians, which is the 60 degree, and if I substitute the values, and we know that cos alpha, that is cos of pi by 6, is actually root 3 by 2, and cos of pi by 3 is actually half. So I'll write the value over here. So I can write root 3 by 2 into 1 by 2 minus, similarly sine alpha is actually equal to sine pi by 6 is actually equal to 1 by 2, and sine beta, that is equal to sine of pi by 3, is actually root 3 by 2. So we can write 1 by 2 into root 3 by 2, and then we can cut these values because they are actually identical, and we find that this is 0. And what is alpha plus beta? That is nothing but pi by 2 or 90 degree, and cos of pi by 2 is actually 0. So we see that this formula actually does work. Okay, and so alternatively, if you want to look at it from a different way, we can derive the formula in terms of sine of alpha plus beta through this figure that I have over here. Or you could also try and get the expression for sine of alpha plus beta from by doing some manipulation in this figure right here. So what we need to find over here is sine of alpha plus beta. So let's actually look at what that might be. This is actually right angle over here. So from this figure we see that sine of alpha plus beta is equal to AD by OD, right? Alright, so before I begin working on this proof right here, I actually want to explain one specific part of this figure over here. I think everything else is pretty self-explanatory. That is as to how exactly I've got an angle alpha in this place. Alright, so we can clearly see that the sum of the angles of this triangle will be equal to 180 degree or pi radians. And since it's 90 degree over here, we can actually say that this over here, an angle we'll allow it to be delta, is actually equal to 90 minus alpha. And since this is a vertically opposite triangle, this angle over here is also delta. I'm not going to write it there because there's no space over there. And so this angle over here will be 90 degree because that is 90 degree, and so this will also be 90 degree. And this angle over here will actually be alpha. Now, since that angle is alpha, and we know that delta plus alpha is equal to 90 degree or pi by 2, this angle will actually be delta, this angle over here. And since again you have a right angle triangle and this angle is 90 degree, we can say that this angle will be alpha. So let's actually proceed with this proof. Now, this proof isn't exactly intuitive because you should know what result you're getting towards. But once you know what that result is, I think it's actually pretty easy to work with this, and it's comparatively simpler than this, I believe. So let's actually begin. Now, what I want in this expression to be, I want this expression to be a sum of two sum of two terms. Like I got an expression of this, like over here, right? I want the expression to be of that form. So using that logic, I'm going to write AD as EE plus DE such that we actually get two different terms. So I'll write this thing over here as EE by OD plus DE by OD. Alright. Now again, using the same logic as knowing what expression you would expect, we can see that we would probably want an expression that involves trigonometric functions, right? So if you look at this expression we have over here, we have AE and OD. So we're likely missing two terms to actually get a trigonometric function, right? One term in the denominator, that would be one trigonometric function, and one term in the numerator, that would be one trigonometric function. So using that logic, we can say that for triangle, for AE over here, we can say that this will be equal to BC, because this is nothing but a rectangle. You can see that each angle is adjacent angles are 90 degrees. So instead of AE, I'll just write this as say BC over here. Okay, I can just write this as BC. Now for over here, if I see BC by OC, that will actually be sine alpha. And so if I were to write BC by OC over here, I'd also have to multiply by OC in order to make it equal. So I can actually write this as OC by OD. And if you look at OC by OD, this is OC and this is OD, that is nothing but cos beta. Similarly, if we look at DE over here, you can see that DC is the hypotenuse of the triangle that contains DE. So I can write this as DE by CD into CD by OD. And you might have probably guessed what this will be, but CD by OD over here is actually sine beta. So if I substitute all the values, I can say BC by OC is sine alpha, OC by OD is cos beta. Similarly, DE by CD is cos alpha, and finally CD by OD is sine beta. And so here again we have a really convenient expression that we'll be using often throughout this chapter or course, or basically all of trigonometry, and that is sine of alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. Personally speaking, I find that this proof is a bit more intuitive, because while you can actually get this expression if you sort of think about it on your own, but over here you actually need to know where you're going. But ultimately speaking, I think it's pretty simple. You just need to divide and multiply by some terms and then you get the answer. But I believe it's only necessary to memorize one, because you can easily derive the other one by simply saying sine of alpha is basically equal to cos of pi by 2 minus alpha, like we just saw up over there. Alright, and so using these two formulas, we're actually going to derive our last formula of this video, and that is tan of alpha plus beta. Alright, so now tan of alpha plus beta can simply be written as sine of alpha plus beta by cos of alpha plus beta. So if we just write that over here, and now we are just going to expand this and we'll try to make it a neat expression in terms of the tan values of alpha and beta individually. So we'll try this as sine alpha cos beta plus cos alpha sine beta by cos alpha cos beta minus sine alpha sine beta. Now, if you'll observe, you'll see that this is all in terms of sines and cos, but we don't actually want it to be that way. So what we'll do is we'll multiply this whole expression by cos alpha cos beta. And you could think of doing this because you want an expression that consists only of tangents, right? And if you divide by cos alpha, you might actually get a chance of getting tan alpha and tan beta. So we're going to divide the whole expression by cos alpha cos beta, and then we'll get tan alpha, because the cos beta gets cut, and we can say sine alpha by cos alpha to be tan alpha, plus tan beta similarly, and the cos alpha cos beta gets completely cut over here, so we'll just write 1 over here, and then the cos alphas don't get cut, but instead they become tangent, so we can write tan alpha tan beta. And so this is our expression for tan of alpha plus beta. That is the tan of a compound angle that has been made up of alpha and beta. So you could also derive the subtraction formulae that are made of by simply replacing plus beta by minus beta for all of these. Suppose if you wanted to get the minus formula, you could write sine of alpha minus beta, and that would be sine alpha into cos of minus beta, that would just be cos beta, plus cos alpha into sine of minus beta, that would actually be minus sine beta, and then you just become plus. So we can actually just write plus or minus over here in all of these, and over here also if I wanted to. Okay, so I think this is pretty much it for this video. In the next video, we'll try and derive a multiple angle formula. That is, suppose you have a sine of 2 alpha, and so other formulae like that, and also the transformation formula, and we'll look at some problems also, I guess. So thank you for watching, and see you next time.